So is my screen visible and am I audible? Thank you. So let us start. Building on the discussions that we had in terms of running multiple kernels on a GPU parallelly simultaneously, we will talk about CUDA streams. So CUDA streams are used. They are basically what happens is CUDA operations, they run in streams. So by default, if you do not declare any stream, it will take the null stream and it is the default stream where all the kernel launches happen. If you explicitly declare any other string, which is a non-null string, here you can create this CUDA stream, and in this string you can launch some kernels. So without streams, what happens is when you are executing your code, it will get added, or when your kernel will get added to the default stream and will start execution. But if you create multiple stream, multiple kernels can execute parallelly. So you also have these two functions, that is CUDA stream synchronize, which will force the host, that is CPU, to block until all operations in the provided stream have completed. Or you can use CUDA stream query to check if all operations have been completed. So visually, if you have not understood what streams are, in a serial fashion, what will happen is if a kernel is launched, first it will copy data from host to device, then the kernel code, copy device to host. With multiple streams, what you can do is, let's say if your host to device copy is complete, the next kernel's host to device can start during the previous kernel's execution. Similarly, if you have duplex, that is, host to device is a different path and device to host is a different path, in that case, you can parallelly execute all three kernels different sections, that is device to host, the kernel code, and host to device, and so on. So here because we used three streams, three of the kernels have started executing parallelly and are able to overlap their execution or overlap different resources. So how do we use streams and why do we need streams is, as we know, PCI bus limits the concurrency. We discussed that in the morning. If the device has a duplex PCI, that is, you can do host to device and device to host at the same time, then we can have different streams, and different streams can be used to do two things in the parallel. That is, data can be transferred from device to host and host to device. So how many maximum number of concurrent kernels you can execute? Again, this you can get based on what is the device. Based on the device capability, there is a count which is fixed for how many maximum number of concurrent kernels can be executed. Fermi device allowed for 16-way concurrency. Kepler device allowed for 32-way concurrency. We'll also talk about how the concurrency, although in Fermi it was 16-way, it did not actually wasn't as fruitful, and what was the solution, and what made it better in Kepler in the next slides. So the stream scheduling happens in this in such a way that the concurrent kernels will operate in multiple CUDA streams, and that will be scheduled by the hardware. In Fermi architecture, the problem was that all streams were ultimately multiplexed into a single hardware queue. So the task at the front of the queue was scheduled by the CUDA, and every time the runtime would check if there is any task dependency and wait for the prerequisite of the task to complete. When all dependencies were satisfied, the new task could be dispatched to a single available SM. And this led to dependency. We'll see in the next figure, and I hope that will clarify what false dependency I'm talking about. So in Fermi architecture, there were two problems. One is it had a single hardware queue. So this is a hardware queue. If there are three strings where A, B, C are the three tasks, that is H to do B, kernel function, and D to H. Because it was a single hardware queue, ABC and PQR could not be parallelized as such unless they were not using the same data, and there were multiple very complex scenarios where it could work, but in most cases it was not parallelizing it. Also, it used to have a dependency between D to H and H to D because it did not have duplex. So you could do the transfer only in one direction. Hence, till C is complete, P could not start. This was a false dependency because of the single hardware queue. Now, with Kepler architecture, hyperqueue was introduced. So Kepler had multiple hardware queues. Hence, and also it had supported duplex. Hence, multiple streams could execute multiple kernels concurrently. So Kepler GPU has 32 hardware work queues and could allocate one work queue per stream. If there are more than 32 streams, then multiple streams will have to share the same single work queue. You can also assign priorities to streams by using CUDA stream create with priority and mention what is the priority here. With lower integer value will indicate a higher priority. So if you want to say that this stream should complete its execution first, then it would give a lower integer value to it. Maybe with 0, it will get executed first, and the stream whose priority is 1, 2, or 3 would be executed after the 0. So this way, you can also prioritize in terms of streams. You also have something in CUDA which is called CUDA events. These events are basically lightweight GPU timestamps, which can help you to measure time on the GPU, synchronize operations between the streams, order dependent tasks across streams. Also, you can enable overlap of compute and memory transfers, and so on. So here, you can think of CUDA events as a checkpoint where the GPU can wait on or report timing from. So how do we use this CUDA events is you can create a CUDA event. This event you can create and destroy once the event has been used. If this event has to be for a specific stream, you have to mention the CUDA event and the stream ID. So this past event can be used to wait for a test for the completion of any preceding operation in the specified stream. If you want to wait for a particular event blocks, and in that case, you can use the CUDA event synchronize. So you can mention the event and call this function CUDA event synchronize, which will wait for a particular event block to complete. You can measure the time of your CUDA kernel using CUDA events. So I'll show you how it is done. Here there is a code. I also have another one. Okay, let's go through this one first, and then maybe if needs we can go through the other one. So here you have created two streams, stream 1 and stream 2. Event is start and stop. So you first create the streams, then create the events, then you record start. So start will start. Then you do the CUDA mem copy, host to device, and then execute the kernel. Once this is done, you again copy the host to device and kernel. Now you've stopped the event. You call again the CUDA event stop. You do CUDA event stop synchronize, which will wait for this to complete. Once this completes, it will stop and it will record what is stop and what is start. Then you have a function CUDA event elapsed time, which will use start and stop to calculate your time in milliseconds. And then you can print this time in milliseconds. I'll show the code. It's a similar code. So here there is a sample kernel, which is just taking the data, input data, and multiplying it by 2. Now this data, this particular kernel, we will first create the event start and stop. Once you create this event, if whenever you want to record this data, in the earlier example, we have recorded even the CUDA mem copy. And here, but what we are trying to record is only what is the time taken by the CUDA kernel. Hence, the start and stop is put before the CUDA kernel starts and after the CUDA kernel ends. Then you wait for the stop to complete by synchronizing, and then you can print your kernel execution time using this particular function. Then you destroy the events and free whatever data you allocated. There are many functions that are available to you in CUDA, which you can use in trying to optimize, try to gain performance, try to run multiple kernels at the same time, considering the whatever resources are available. A lot of things can be done, but these are some of the important features of CUDA. You also have this function, which is like when a sync engine count is equal to 1, the GPU can only one copy. It can be one copy engine, so it can either do H2D or D2H, but not simultaneously. When you set the async engine count is equal to 2, the GPU can perform host to device transfer, perform device to host transfer, and also run kernels all concurrently, as long as they are in different CUDA streams. So there are many such features which are available to you, or functions that are available to you, with which you can parallelly run multiple kernels and also improve the performance of your application. In the morning, I was talking about device query. So this is how a device query looks like. This is some part of the device query. So here you can see this. I ran this device query on ADA Lovelace GPU, RTX 5000 ADA. The CUDA driver version here was 12.9. CUDA compute capability of this GPU is 8.9. You have total amount of global memory, which is 3229 megabytes. This has 100 SMs, each with 122 CUDA cores. So total you have 12,800 CUDA cores on this GPU. The clock rate maximum is 2550 megahertz. Memory is 9001 megahertz. The cache size, you can see L2 cache size is this. What can be the maximum texture dimension is here. What is the total amount of constant memory you have? The total amount of shared memory per block that you can assign is 49,152 bytes. Total shared memory per multiprocessor is this much. The total number of registers available per block are 65,536. The warp size is 32. Maximum number of threads which are allowed for multiprocessor is 1536. Maximum number of threads per block can be 1024. The maximum dimension size of a thread blocks can be 1024, column 1024, column 1024. So this way, this device query that is available sample in your CUDA toolkit, or if you just Google the CUDA toolkit samples, you will get the GitHub link in which you have this device query already created. You'll have to just compile it, make it, and execute. And it will provide all the necessary hardware related and program related details which you need, or which will help you to design your application specific to your hardware. Another part that we discussed in the morning was profiling your CUDA application, how important profiling your CUDA application is. So you have both GUI and command line profiler for CUDA kernels. Using this and the profiler which you can use it inside compute. With inside compute, it provides you details per kernel. That is, what is the memory throughput, what is the achieved occupancy, what is the SM utilization, warp efficiency, vectorization, etc. And this helps you to see what is on paper or what is theoretical and what you are actually getting or what is the actual performance. So why do you need to do profiling? Is without profiling, we are trying to optimize the application blindly without knowing what exactly the problem is. With a profiling like NCU, it gives you the bound by memory bandwidth, arithmetic throughput, or any kind of thread divergence that is happening. So, for example, you might think that the program that you've written is a compute bound program. A lot of computation is happening. But after profiling, it might show that it is actually the problem is not computing. The problem is memory stalls which are dominating the execution time. And your program, which you thought is a compute bound or more of computation, was actually bound by the memory instructions that are part of the program. So this helps you to, do targeted optimizations and not just guesswork. So how do you use NCU? Is by simply do NCU.a.out. So this was a video. So I think I'll just check. I think I added a video here. Is a video. Yeah. So I just typed NCU and provided it as executable. It could be a dot vect add, which is a vector addition executable. And just by typing these two things, see how much profiling data it produces. So some of the things that you saw here include this is done. Like the basic launch statistics of a program, which is what is the block size, what is the grid size, what is the if there is any specific preference or not. We discussed this in the morning. How many registers per thread are being utilized for your particular CUDA kernel? What is the shared memory configuration size? Then how many threads are being run on the particular SM, which is 50,174. Then what is the stack size? How many waves happen per SM and all that. So again, in terms of occupancy, this particular kernel had an occupancy of 25.84. So what is the block limit on SM? How many registers are there? What is the shared memory limit? What is the number of warps that are launched? How many theoretical active warps per SM were executed, which was only 48 in this case. And although we were expecting 100% occupancy, what we achieved was 25.84. And active warps per SM were 12.40. Whereas what is supported is 48. In this particular kernel, what we gained was 12.40 active warps per SM. Then you can also get the details like what was the DRAM frequency, what is the SM frequency, how many cycles for which the execution happened, what is the memory throughput, what is the DRAM throughput. Then this is the time. So this kernel ran for 3.74 microsecond. Then the cache throughput, how many total number of active cycles were there per SM, what is the compute SM throughput. The explanation of what each feature is or what each matrix is also well defined and well documented on the Inside Compute website. If you visit, you will get all these details. So similarly, these are about GPU and memory workload distribution and so on. So I have another video to show to you all where it talks about profiling it using pointer. That's not okay. So this is how the profiling tools can be used either through a command line, that is NCU, or through the UI that is available to you, and with which you can understand what exactly happening when the CUDA kernel is executed, because this profiling data is collected by running the kernels multiple times and taking data from the actual hardware counters where they are executing. Hence, profile data is the most accurate data that you can get in terms of your execution of your kernels. So moving on, any doubts so far? Anything? Okay. So moving on, we will now mostly the whatever I wanted to cover with respect to CUDA in terms of how to design the CUDA application, how to choose the launch configurations, how to decide which type of memory to be used, how do you use that type of memory, and what are the possible um, performance issues with memory we've seen. And we also saw CUDA events. We saw CUDA, learned about CUDA streams. And now we will talk about a few optimizations in CUDA, which are which uh, I'll not be able to cover uh, many, but a few, so that you will know how to, when you are designing your code or application. And these are not, some of them are specific to CUDA, some of them are not very specific to CUDA, but they are also can be used in other programming languages as well. So we'll talk about a few optimization strategies. So the first one is is understanding the problem and breaking it down correctly into serial and parallel workload. So why this is important? Because when you are trying to analyze the program, you always have to consider the time take for this program. That is, what will be the effort that will be put by the programmer, what is the programmer's time, and what is the speed up that you are achieving by utilizing this programmer. Because programming effort, as you all know, is quite expensive. So if a programmer is putting these many hours, is it worth in terms of the speed up that you are gaining? Or if you buy some, faster hardware, will that provide you, will that be a better option? So in such a scenario, you will like to profile your code, identify what are the bottlenecks, where can you improve, is putting efforts by programmer make sense or not, and accordingly take the call. The value of the problem, how do you divide this problem into chunks which can be run parallelly? How the design considerations are for a particular problem. So, for example, if you want to do, let's say, sorting, which algorithm of sorting provides you the maximum scope for parallelism? You cannot say, okay, quicksort is or merge sort have the best, you know, best time complexity. So I should use quicksort or merge sort. But is quicksort parallelizable? May not be. There could be other sorting algorithm which are in otherwise not so efficient, when you do them serially, but have enough scope for parallelism. So, can you construct a formula which will represent the value of a given output point and then create a transformation to the input data set and understand if this problem decomposition works or not? So, what is critical here is whenever you're designing a parallel solution, you must fully understand the problem. Understand what are the places where you, or what is the scope of parallelization that you have for a particular problem. So one of the optimization that you must consider is when you are trying to design a function. Let's say here in this particular example, if you see, you have a is going to be into 100, c is going to be into 1000, and then d is equal to a plus c into e. Okay. In terms of parallelizing this code, these 3 lines of code, do you see a issue in terms of how much parallelism you can achieve in this? Maybe you can execute this and this parallelly because they are not dependent. But this instruction cannot be executed parallelly, right? Because this instruction is dependent on the first 2 instructions. So when there are dependencies, that is, if some calculations require the results of previous calculations, this can cause a number of stalls in the pipeline. Because unless you get the results of these 2, the pipeline, although was filled with this instruction, cannot proceed because it needs the results of the previous 2 instructions. So you will have to just stall the pipeline. Can you think of a solution like, or can you think of what can be done in such a scenario so that we can avoid these stalls in the pipeline? Okay. So what you can do is, when you design a function, try to add a lot of independent instructions before any dependent instruction. So here, because there is f and g after a and c, here is where till these instructions execute, you need not execute this instruction. And when you have these different independent instructions, you can achieve a lot more parallelism or a lot more better performance. Another technique that is there is loop fusion. So here we have loop fusion. So we have, in this particular example, can you, as the name suggests, fuse the loops, and can that be that can that help? I don't think at least CUDA streams are fine, but this, I think you all can answer and give me some examples or what can be like some suggestions on how can do things better? How can we optimize? In this particular example, am I audible, right? Okay. So we are learning about loop fusion. Okay, why anyone can tell me why loops are a problem? Means loops are good, but in terms of programmability, but loops are also a problem sometimes, because in loops, what happens is you first check, assign something, but then you check a condition and you branch. So a lot of branch is. Oh, you all are muted. I'm really sorry. I didn't know that. Okay. I think now you can unmute yourself.
Yes, ma'am.
Okay. Yeah. Yes. So because yeah,
Ma'am,
because yeah, yeah. Go ahead.
in this case, like parallelism, like we are looping, we have a two loops, so we can just do the parallelism two times. So we'll not get the benefit of the parallelism here.
Um. Okay. Um.
Means these are the two blocks, so we can do
Yeah,
just
but can you fuse them? And is it possible to fuse these two for loops so that we avoid a lot of branching?
Ma'am, calculation
Because
of
A and D are independent, right? Yeah. Yes, Yuvraj. Yeah.
yeah, calculation of A and D are independent, as you rightly said. A is
Yeah.
dependent upon BCI while D is dependent upon EFJ. So they both can be done in parallel. So first for loop, which is running for 100 iteration,
Hmm.
can take care of computing A as well as D
Hmm.
together in single block.
Hmm.
And the second for loop can be executed only for 100 times.
Okay. So you're suggesting this solution.
Yes, that's
Okay.
correct. That's
Hmm.
correct. Yep.
So, but uh, can you do something better than this? Can you think of something better than this?
Next would be
um,
to fuse, sorry.
Yes.
Next would be to fuse both of them together and have a conditional check inside the for block for computation of A. If that index is less than 100, then only A will be computed. Otherwise, it will not be. So that way only, as in only one for loop will be there, which will get executed 200 times, and A will be computed till 100 index, and after that it
Yes.
will be skipped.
But using if will again is branching, right?
Yeah, again it is branching. Yes, that's true. Hmm. Yeah.
So another solution could be this. Yeah, adding to D in the same loop by with both 100 as well as 100 plus I for the next 101 to 200 as well. So this way you can fuse the loop further.
Yeah, true.
Hmm. Okay, so we should try to fuse loops, avoid as much branching as possible, because then the problem of stalls, and then the problem of uh, very limited independent instructions come into picture. So fusing the loops is a good optimization technique.
Ma'am, one question on prior slide.
Mm.
Uh, the two lanes which are computing D for first portion of it, we are seeing EFI, and
Mm.
then for second portion, we are seeing EFI plus 100. So we are taking care of two indexes in one go, as
Mm.
part of one loop, I mean. But
Mm.
here, computation of D on the
Mm.
middle line,
Mm.
and same variable is getting updated on the next line. So wouldn't that kind of have a problem that way in context of parallelism? Because D will be referring to same memory location, right? So we are trying to uh, write at the same index via those two statements. Wouldn't that cause any problem per se?
Mm. Yes, you are right that D and both D's cannot happen parallelly
Right.
because they are trying to do try the same memory location.
Mm-hmm.
Yes, that I agree.
So until the middle line execution is complete, we won't be able to execute the next line that way.
Yes,
So how
yes.
that will help us in increasing the speed?
So it will increase in terms of reducing the loop overhead, not providing because see fewer loops will mean that we are having less overhead from all the loop control statements that are there. Again, also in some cases, if instead of E and F, it was some array memory location, okay, which is repeated here and here in both places, okay, then it would be that because of data locality, and we are accessing this twice in the same loop, even the caching will help because it is recently being used. That way, it is with loop fusion, you can also get improved data locality.
Yeah, get you. Get you. Sequence dependency is there, but there are other factors which are going to help
Factors.
the execution is what you're trying to comment.
Yes. Yes.
Okay.
Yes.
Okay.
Thank you.
Thanks.
So dataset size is also a very critical feature in terms of performance that you can get get on your GPU. Because if the dataset can fit within L1 cache, that is 16 KB to 48 KB, it has the least latency, so it will be most it can be executed with the best performance because of very little latency due to memory access. If it goes to L2 cache, it will slightly take longer. If it is in the GPU memory, that is global memory, we know that the number of cycles it takes is up around 600 to 800 cycles. It will be slightly costlier and the performance will degrade. If the data set is on your CPU memory and you are trying to access this CPU memory from CPU using PCIe, again, it will take longer than the transfer that you need, time taken on from your GPU. Similarly, if the problem is very huge and one CPU cannot fit in the whole data, you distribute the data amongst multiple machines and the data is more than, let's say, 20 TBs, it will again affect the performance. So data set size is also a very important critical factor in terms of how much data set you are working on. You also need to identify the bottlenecks in your code. That is, we learned about Amdahl's law, if you all remember. So when the program had 50% of this program was serial, and if you had infinite number of processors, how much speed up you could achieve with Amdahl's law? Anyone remembers?
Not more than 25%.
So that is, you can maximum use two, although you have infinite number of processors, you can maximum use only two processors, because beyond that you cannot use a number of processors, because 50% of your program is serially executed. Even having multiple processors is of no use. Hence, if let's say if you have a problem like this, where you can imagine this problem to be like a field, and these are like tractors are moving in this field. Okay, and these are the gates which you can imagine to be serialized execution. When these tractors are moving through these gates, and there is a single gate for this tractor, what will happen here? Because there is a single gate, they will do serialization. That is, they will pass through this gate one at a time, right? And if you know such a bottleneck exists, how can you fix this? This particular problem of tractors moving in a field? If there are these gates which are serializing the or being the bottleneck and are serializing their passing through. Instead of having one gate, you can have multiple gates, right? So you can remove this bottleneck and have multiple gates. In that case, the parallelism will continue. Similarly, you should find out what is the problem, what is the part of your code which is serializing the problem, that is, which is being the bottleneck, and remove this bottleneck and ensure that your code is being executed parallelly by multiple resources, and this is how you can have a better performance for your code. Profiling we just discussed, so I'll not talk more about this. Is again an important factor in this strategy. So in this strategy, what we talked about is what is important is understand the problem and define what you want to achieve in terms of speed up for this particular problem, and how much programming skill that you have, and how much you can afford to utilize for your particular problem. Then identify the parallelism in the problem and think about how best to allocate this between a CPU and one or more GPUs. About what is more important, lower execution time or processing the data at a higher resolution. Understand the implications of if there is any serial code section that you have, and think about how these might best be handled and how these bottlenecks can be avoided. Profile your application to ensure and understand that what you think, how your code is executing, is what is reflected in the actual reality or actual execution of your code. Repeat your analysis if needed, and with that, change the code, repeat it, change the code, repeat it, so that you have better understanding of what is happening in your application. The second strategy, with maybe let us take a 5 minutes break and then continue with the second strategy. I think that will be better. So it's 6:57. So let us meet at 7:05 and continue. So let us continue our discussion on the optimization techniques. The second strategy, some of it we have already discussed in the morning, is about memory considerations. Because memory bandwidth and latency are very critical, because uh, without data movement, we cannot do any kind of computation that would be useful in most cases. And memory is a bottleneck in terms of performance, because as we have discussed this multiple times, the time taken to move any data from your global memory to your registers, or for any computation, takes almost 400 to 600 to 800 cycles. And if you store your data in shared memory, the same thing can be done in 30 cycles or 35 cycles. So this memory bandwidth and the time taken to latency is very critical when it comes to how many memory operations are part of your CUDA code. So in GPUs, we are concerned about mostly global memory bandwidth, because the shared memory latency is very negligible compared to global memory. And how the memory latency is expected to be hidden is by GPUs have to run multiple threads from other warps. And when a warp accesses a memory location which is not available, the hardware will have to issue another warp, which which takes care of its overlapping the execution of warps and ensures that the hardware is always doing some useful work. So also, we when we submit such a request, we expect it to combine or get coalesced with other requests from the other threads in the warp, and ensure that they are fetching the data from adjacent memory locations, and this access is aligned so that caching can help to overcome the latency that you observe because of global memory. So we discussed about the what are the coalesced and uncoalesced accesses. So if there is coalesced access, you get 128 bytes of data from your global memory, fetch it, so it gets cached also. So when the first thread is needs data of first memory location, which takes time to fetch, the second thread, whatever data is needed, is available when the first data is fetched. So if your threads are accessing data in consecutive memory locations, you get a much better performance, instead of if threads are executing or are fetching data from unaligned accesses or random accesses. We can also save on memory bandwidth using loop fusion, as we just discussed. So if you have also, you can fuse kernels. So if you have number of kernels which can run in a sequence, if you combine some elements of it and fuse it, it might give a better bandwidth, because anyways the data is being fetched in one kernel. If it is feasible, it may or may not be feasible all the time, kernel fusion, but if it is feasible, try to have minimum number of kernels so that the bandwidth issue gets does not become the bottleneck, or does not become the performance uh, constraint. Try to use shared memory and cache as much as possible, because shared memory provides at least 10 is to 1 increase in speed over the global memory. But the problem with shared memory is it is limited in size. You have a fixed size of shared memory that is available to you, and you can use only that much amount of memory. Shared memory runs at the speed of L1 cache, and hence it is one of the fastest alternative to your global memory. We've seen how you can use shared memory, that is by using a shared option, which is a shared type qualifier. Wherever you put this, this data gets stored in your shared memory. Then you can fetch any data from your global memory, store it here in your shared memory, and then do the computation. And once the computation is done, then move the data or result back to your global memory. So for the part where computation is required, that happens in your shared memory. So you do not waste every time, you do not try to fetch data from your global memory. And this significantly helps you to improve the performance. The problem with shared memory is bank conflicts. So you must avoid bank conflicts as much as possible. And to avoid bank conflicts, you can use padding if your particular problem allows that. You can go ahead and use padding, and that helps with bank conflict. If you are using fetching data from external devices, then the IO, or if you're trying to connect coordinate with other external IO devices, the IO bandwidth also is important and a critical criteria for gaining performance. These are the issues or the important criteria to be considered in terms of memory usage. In the third strategy, we'll talk about thread usage. What are the calculations with respect to thread usage and divergence? To start, we must consider what is the arithmetic density of your kernel code. What do you mean by arithmetic density? It is the measure of number of calculations per memory fetch. So in this particular example, C of z is equal to A of y into B of x. So for one multiply, you are doing 2 fetches, right? So here the arithmetic density becomes very low because 2 fetches, if they are from global memory, they might take around 800 cycles. So 800 cycles spent to fetch this data. So 600 cycles. And how much time your multiply will take? If it is integer multiply, it might take around 15 to 30 cycles. So you are comparing 30 cycles to 1600 cycles spent in fetching data. So this particular kernel, which is trying to do this computation, has a very low arithmetic density. And such a kernel where there is a lot of time spent on doing memory operations is called a memory bound kernel. Because the total time is dominated by read time of A and read time of B, and then storing of C. After the C is computed, you store back C. You can use something known as transcendental operations, which are special operations which are available to you, which run on special function unit, which is built in GPU and which is meant to do these specific functions. So this dedicated hardware is designed or it's optimized to do the computation for such computations much faster. You can use this using the dash use fast math. And these are the different transcendental operations that are available to you in CUDA, which could be a division, square root, reciprocal square root, sine, cosine, log 2, base 2, exponential x2. So there is a special function unit which is available on your SM, which is a hardware unit, which is optimized to do this competitions much faster than you doing them on normal codes. So you should use these tangential operations wherever possible over writing, simplified version of these functions, because these are optimized for use. So the CUDA SDK earlier used an Open64 based compiler, and then they moved to LLM based compiler. And this movement claim, the NVIDIA claimed that they have achieved 10% improvement in their code speed. So we'll see some of the compiler optimizations for CUDA that are possible. So one is strength reduction. When you're trying to access some array, what we typically do is the array element is equal to index into element size, right? Can we replace this with something which is cheaper or which will be done faster? We can either load the array base address into a base register, and then we can just get the base plus offset and read the data in a loop. So this is what I'm talking about. Can anyone tell me how this is better than, which of the two is better?
I think the second one is better.
Yeah. And why is it so?
It's accessing the low level address directly.
Low level?
Low level address it is accessing and then storing the values. Low level address of the, it is utilizing pointer.
So the difference between the two is here we are doing a of I is equal to I. So here what is happening is every time we are taking the index and multiplying it by element size. Okay. For every time we fetch data, we are doing the calculation of index and then, updating this data.
Yeah.
Instead, if we create a pointer, here the operation is just pointer plus plus, only addition. So this is much better in terms of performance compared to trying to fetch data every time. Is it clear how this is better?
No, ma'am, it's not clear. Can you explain me again one more time?
Yeah. So this is, we are trying to fetch data array of I, okay, or update data array of I using I. Every time you are doing this, what you do is you compute what is the A of I. So address where you are trying to update, which will be index, right? Which is index into what is the element that you're trying to access. Okay.
Okay.
Which is multiply operation. Okay. That you are trying to do every time. Instead, you use a pointer which has the address of base, and every time you are updating this particular location, you just do a plus plus.
But if you see at the low level here also we are getting the address of ith element in the array and updating the values. And in the second program, we are incrementing the memory location and updating the values.
Can you repeat?
In the first program, what I'm understanding, we are AI is the basically memory location of ith element of array A,
Yes.
and we are assigning one value.
Yes.
And in the second program, we are just like creating the pointer of first element of array, and then we are incrementing. We are doing one operation to get the next memory address to assign the next value of the I.
See, when you're calculating effective address with A of I, what you do is you take the base address, right,
Yeah,
of
plus I.
your array, huh?
Yeah.
Then you take index of I. What is the I, right?
Yes.
And you multiply it by how many number of elements are there, size of elements. What is the size of each element?
Yes. Yes. Yes.
Okay. This is how you compute.
Oh, got it. Got it now. Now it's clear. Basically, here we are doing more arithmetic operation
Yes.
than the next one. In the next one, we are just doing one plus, but here we are multiplying. Arithmetic operation is more in the first program.
Yes.
Got it. Got it.
Yes. Yes. So hence in this particular case, pointer is better for memory manipulation, especially when you are dealing with data structures where the you know memory access is being performed directly. Okay. So in terms of GPU usage, in with respect to strength reduction, what you should do is try to use uh, certain instructions which are computationally expensive, avoid them, and use the instructions which are cheaper. So you can replace, because multiply and add are computationally expensive in terms of how they are executed on hardware, and they take more number of cycles compared to add or sub instruction. Another optimization technique is loop invariant analysis, where you are trying to find expressions which are constant within the loop body and you move them outside of the loop body. So in this particular code, which is the operation, which is the instruction?
Computation of B, no. That can be
Huh? Yes.
computation of B.
So this can be moved out, right? Okay. So we can do this. If we move this out, then B will not be calculated multiple times simply, right? Correct?
Yeah, that's correct.
Now, this you can say a compiler should be easily able to find out and fix this, right? He will optimize
Yes.
it. Compiler will take
Yes.
care of optimization. Why do we bother in this particular case? This is fine. This can be taken care of by compiler. But if you have such a scenario, what will happen? Do you think compiler will do this optimization themselves?
Not really. Not really, because B is outside, so compiler won't be able to understand. I need, or it will not be in a position to decide whether I can optimize it or not, and it will not, I think, in this particular case.
And such cases, the programmer will have to take the call.
Right.
And we cannot depend completely on the compiler to fix such cases. Correct?
Yes, true. True.
Another technique is loop unrolling. So here, why you need to unroll the loop? What is loop unrolling is, instead of doing only one instruction inside a loop, can you unroll the loop? Can you make the loop slightly bigger? That is, See, if you have this kind of a loop, what you will do, how this loop will execute, you will load a register with 0, you test with 100, branch or exit depending on the test. Then you increment the loop, then you do the address calculation for the array, and then store this value of I to the calculated address. Instead of this, can you do this? I think this has to be. Here, what we are doing for the same number of comparisons and number of instructions executed, because of unrolling the loop 5 times, we are avoiding the same instructions being done 5 times. So this is much better in terms of the performance over what we did in the earlier case. However, the size of C code has now increased, and it is not very, for if you just look at the code, it will take you some time to understand what exactly is happening. So it is not as obvious as it is here. Although it's doing the same thing, but it is more optimized in terms of the performance of code. This code.
So, ma'am, this I should be 25 here, no? Why it's 100?
Which I
In the right hand side, I should be
Mhm.
less than 25 because in one iteration we are calculating 4 cubes. So we just need 100. So that should be less than 25 only.
No, but I you are incrementing by 4, na? Every time.
Okay, okay, got it. Yes.
So in terms of PDX code,
Ma'am, one question on earlier slide.
Yeah.
We are just flattening the for loop to some degree, if you see it that way.
Yes.
It is kind of sequential only, right? Instead of, let's say, having 4 indexes getting computed within loop, I'll say I'll compute 8 indexes and I'll increase value of I by 8.
Yes.
Wouldn't that kind of flatten the code to a good degree?
Flatten, as in,
As
it
an
will increase the
increasing
size
number
of the
of,
code,
yeah,
right?
number of statements are kind of increased in for loop, which do not have much meaning that way.
No, but it significantly lowers the number of times the CPU executes the control instructions, the loop control instructions, that is incrementing the counter, checking the condition, branching,
Okay.
jumping back to start. It also reduces branch penalties. That is, since we have fewer jumps, means fewer potential pipeline stalls, right? It
Okay.
also
So,
increases instruction level parallelism because if you can, place more independent instructions, the compiler and CPU can schedule more, instructions also. And all these are because they are accessing different memory locations, they are kind of independent.
yes. Yes, so we are kind of trying to balance between the time which we need in order to run one loop, as in branching and all,
Yes.
against how much time actual execution of that for block takes. So we are kind of trying to balance that out here.
Yeah. Yeah.
Okay, okay. Then why 4 then? Question would be why 4? Why not 8 or 16?
No,
How do we decide how we can increase the benefit here?
okay. That you can decide uh, by um, balancing what is the gain that you are getting from this reduced loop overhead and this increased parallelism against what is the penalty of the code size, and how many registers you need, because unrolling will need more registers, right? Compared to the earlier code. So it will put some pressure on register as well as cache. So this is also very important.
Okay, how many
So
registers are
common,
available?
yeah.
How many computations
How
could be
much?
done?
Yes.
I agree.
So
Okay.
usually it is done in like 2, 4, 8 or 16 is what they choose, because that's how we even we try to, like, it matches with the power of 2, and that's how we usually have, like, in number of walks and or the data sizes that we have. That's why.
Okay. Okay. Get you. Thanks.
So uh, so if we run this, there for every branch test we have 4 memory copy operations. So GPU is executing more instructions than before, and it also has higher percentage of memory copy operations which are doing useful work. We also, the limit is the number of registers, as I just discussed. If your GPU has sufficient registers, you can have considerable scope for unrolling, and that should help you gain good speed up. And VCC compiler also provides you hash pragma unroll directive with which you can, unroll. So this asks for a number, and based on the number, it will unroll. Another technique is loop pinning. So in this technique, what happens is when the number of iterations are not exact multiple of the loop unrolling size, in that scenario, loop pinning comes into picture. If the loop is cannot be unrolled exactly with the same number of loops iterations, then what you do is either the last or first few iterations you can peel away, and they can be done separately. So for example, if you have 101 loop iterations and you want to use 4 level of loop unrolling, the first 100 iterations can be unrolled and the final iteration can be removed and done separately. So for example, here, so what it will do, even the compiler, CUDA compiler, if you use hash pragma loop unroll n directive, it will unroll the loop, and the extra number of iterations which cannot be part of the loop, it will put them in the end automatically. So for example, here, what is filled here is the first iteration is removed and the remaining are kept in the loop body. So with this, this technique is called as loop pinning, which is can be used over the loop unrolling if the number of iterations cannot be divided amongst the number of iterations cannot be divided as per the amount of operations being performed. Another thing that we need to think about, or we need to know about in terms of performance, is divergence. What happens in a warp is when a single instruction is decoded and it is given to a warp scheduler, the warp scheduler will then dispatch these 32 one instruction to 32 threads, right? The 32 execution units that we have. Now, when these 32 instructions are executing and they encounter a branch in the code, in that time, if only some instructions follow this branch, those instructions will diverge, while the others will wait at that point of divergence till the rest of the instructions complete. So, how do you think this will degrade the performance? or why this is a critical factor to consider when you are designing your code?
Some of the threads out of 32 will not do any work. So that's kind of no op for them until other threads complete their work and
Yes.
come back.
Yes. So
Okay.
the divergence. So what happens is when, for example, when there is a single fetch decode logic which fetches the instruction stream for the divergent threads, and other threads simply ignore it. Each thread within a WOP has a mask which will say either you execute or does not execute. So it will enable those who need to collect this data, and those who are not following this divergence will have the mask cleared. So because of this type of arrangement, we call this arrangement to be predication. A predicate is created which results in a single bit being set for those threads within a WOP that follow the branch. So in this particular example, if you see, so here, first we check if thread ID is less than 32. Here there is no divergence happening. Why it is not happening?
Total number of threads within a
Yes,
block are going to be 32.
within a wall, within a wall.
Within a WOP, sorry.
Yes, are 32. So here there is no divergence happening. Then when you come here, the first WOP then meets this test, and it will split into exactly half. Okay, but this divergence also does not happen because CUDA codes are arranged in banks of 16 and not 32. And hence, the scheduler will issue instructions, two or more sets of 16 codes per cycle. Okay, so both true and false path can be executed. That is not an issue. But here, when you divide now, the here is where the divergence will happen. The first set of threads will jump off to call and function this function A, and the rest will wait and do the function B. So here, function B and function A will continue to execute independently, okay, and dispatch whatever instructions to these two halves. But what this is inefficient because a single instruction fetch will not happen for a particular WOP. The rest of the WOP will have to wait. So we will see the results of how it looks like. So
Ma'am, can you please
here,
repeat that one more time? That wasn't
okay.
clear. The divergence part, particularly once we get inside that if and else, A1 and A2, that portion
Yes,
particularly.
yes. Here, those which are doing thread ID x.x less than 8. So first 8 threads, when they are executing, the remaining 8 will wait. Then they'll come here. In else, the remaining 8 will execute. The first 8 will have to wait. Because the instructions that we assign are assigned to the whole WOP. Hence, two different instructions cannot be assigned to a single WOP at a time. Only thing
Okay.
that will happen is they'll be masked to say that you don't do anything. You assign this instruction, but you do not do anything. So what will happen is here the first 8 will get stalled, second 8 will get stalled, and here that is 8 to 16, and here 0 to 8, 0 to 7 will get stalled.
Okay. Okay. Because all of them are going to get execute only one instruction. Instruction is going to be exactly same.
Yes.
Uh, Scheduler will just say for
You execute it or not.
function call A1. Yeah,
Hmm.
only zero 0 till 7 will execute it. Actually, others will skip it in a way.
Yes, yes,
And vice versa when we go to
yeah.
else block. Okay. Okay.
So if you see these results, we are running 32,768 blocks of 32 threads to calculate these many elements in this particular example. When you have all threads, the execution time is 27.05 milliseconds. When you do half pop, it becomes 32.59 milliseconds. Quarter walk, the performance degrades significantly. And eighth walks, it degrades further. Same you can see on different GPUs being executed. The performance gets significantly affected when you have these, you do the divergence for half hops, quarter hops, and eighth hops. This
Ma'am,
is
here half warps on the prior slide.
Hmm.
When we say half warps, we mean half of the threads within that
Yeah,
warp are
there is
executing the
16,
instruction,
16,
half of them are
16,
skipping it.
16. Yeah,
Okay,
16.
okay, got you. Got you.
So this is the figure, how the performance degrades. And it is quite consistent across the GPUs. So branch divergence is a very critical criteria for to be considered for the optimizing or while designing your code. What do you think is the solution, or what you should do to avoid this?
Ensure that you write program in such a way that all threads will be executing the instructions. As in refactor the code in such a way that every thread has to execute that instruction as much as possible.
So whenever you have conditional statements, try to have them by 32, right?
Oh yeah. So that all the threads will get the work. So number of threads.
Have the divergence at warp level,
Warp level. Yep. Agreed.
not interval.
Yeah.
Ma'am, in addition to this question, there is on second blocks, 9800 GTX. We are not seeing a lot of variation while doing the all thread, half warp, quarter warp. But if you see first and last, there is a lot of variation in the performance.
Yes, I agree.
Uh,
So,
what is the reason behind this? It's because of
uh,
architecture.
so let me just. It is the I can't recollect the exact thing, but it is the architecture which is the reason why this is. I think yeah, it is in the CUDA programming model. We just select the divergence part. So here, this is the CUDA programming book for which has this optimization. Yes. So thread divergence was not significant on the compute devices 1.x, that is 9800 GT and GTX 260. But with a newer, that is 2x cards, these suffer over a 4x slowdown.
Yes, yes. It's because of architectural design of those
Yes.
devices.
Yes. With more complex means 1x is the first generation, right? So
Yes.
with second generation, it became more significant. They should become more significant. There are many other techniques of optimization. If you are interested, you can go through this book, which is a popular book for CUDA programming by Shane Cook. And it has nice examples and these different, scenarios shown of how you should design a CUDA program, how you should optimize it, and what are the possible choices you should have in terms of different, features for your kernel. So I think with this, we can stop today. Any other questions? And
This book is there.
in the PDF is available. If you search, it will be, or I'll upload it on the Conta. If I'm not uploaded, I'll upload it on Conta.
Yeah, if it's uploaded or if you
I will
can
check.
give the
I've
full
not
name, it
recollect.
will help us to search. Yeah.
No, I will upload it.
Okay. Ma'am, some of the programs that you have shown, right? I mean, in a Word, in a Notepad. So those also, if you have get them full program. So
Sure, I'll upload them also. Yes, I'll upload the two programs that we discussed today on Conta. I meant eLearn, sorry.
As well, ma'am. As soon as lecture is finished, whatever PPTs are there,
Yeah,
please
I'll
upload them
upload
as
them.
well. Yeah.
I'll upload them now. Yeah.
Yeah. Thanks.
So as we discussed in the morning, those who are not present, we are planning. What I'm planning to do is for your compre, there will be whatever we covered after midsem and only OpenMP from pre-midsem.
Okay.
I'll announce that on the
so
eLearn.
all after midsem, everything will be there. Before midsem, only OpenMP, right?
OpenMP. Yes.
Okay.
Yes.
Thank you, ma'am.
Ma'am, is that the pattern which is generally followed? I thought comprehensive would be like all the sessions for the entire course
At
kind
No,
of
least
no,
a thing.
actually, ma'am
no,
reduced the morning we discussed. So yeah.
I think
Okay.
you missed that class.
see, considering that we have learned
Which
too many programming models in this course, and it is although it is open book, it will still be difficult to remember every programming model and its different all the different features it has. And so I felt that I should use one CPU or one shared memory model and one CUDA, and a bit of the Hadoop will mostly be it will be more theory kind of questions.
Okay. Okay.
Yeah.
So you're specifically following this pattern. That's not kind of a journal norm is what
No,
you're
but
trying to
on
convey.
on campus also, I usually pre-midsem I prefer doing shared memory and MPI, and post-midsem it's CUDA and design techniques that we cover usually, parallel program design techniques. But your syllabus did not have design techniques, so hence I'll continue. I'll have a few questions on OpenMP, a bit of Hadoop, and whatever I cover in next two classes along with CUDA.
Okay. Perfect. Thank you. Thank you.
Yeah, thanks, ma'am.
Yeah. Thank you. I'm uploading the slides as well as the codes now. And the textbook also. I'll
Yeah.
just
Thanks.
check if I uploaded the Pura textbooks, but let me verify.
Thank you, ma'am.
Thank you.